great pleasure. Okay. It's my great pleasure to introduce Simon Arridge from University College London. Simon is a great expert in inverse problems, internationally very much respected, and has done some really pioneering work, for instance, in photoacoustic tomography, but in general, in imaging methodologies, inverse problems methodologies related to medical physics type of problems. And in the last, I don't know, couple of years, 2, 3, 4 years, has really gone into exploring the potential of deep learning solutions for solving inverse problems. And on the other hand, understanding deep neural networks better with some of the things that we have been developing in the image processing world. And that is, I believe, what he's going to talk about today, in fact, is unlearned solvers for forward and backward image flow schemes. And yeah, I really look forward to your talk, Simon.
Okay, well, thank you.
This talk is being recorded, so if you don't want to appear in the video, please switch off your own video.
Okay, great. Thank you, Carola, for the kind introduction. And thank you, everyone who turned up. And apologies, this moved from the regular Tuesday morning slot, which I can't make. So thanks for coming, especially today, which is out of the regular schedule. Great. So, I'm sorry. So yeah, let's talk on learned solvers for forward and backward image flow schemes, and many people to thank over the years. But in this talk, I'm mainly talking about work done with these three co-authors. Faculty member at University of Ula and part-time appointment at UCL. And I won't mind, there was finally a student has completed his degree. So here's the outline of the talk. And so I'm going to be talking to a large extent about diffusive processes, nonlinear and anisotropic diffusion and imaging, but we also have extended some of these concepts to a few other flow schemes, which I'll come to. Okay, so let's begin. So in general, talking about how deep learning can be used in inverse problems. So the general definition would be, can we find a, oh, sorry. I need to talk into the mic, apologies. So if we concerned with, let's say, a forward problem here, we want to say that we have a mapping from spaces X, Y, and in general, we would set that up through physical principles, but we want to include the possibility of that being defined by a parametric mapping where the parameters may be learned. And so, generally speaking, and many of us are interested in this idea of how can learned models replace physical models? Should they completely replace them at one extreme, or be completely ignored at another extreme, or how can they be combined? And this is intimately caught up with the question of what there's some chat about. Okay. What are appropriate architectures for learned model, and what? How many? And there's quite a lot of work in this area. just a few to mention here. Some work from 2015 by Chen Yu and Pok on learning optimized reaction diffusion processes. Many of us know the pioneering work of Wayne and Yi on machine learning via dynamical systems. Rudoto and Haber, that Haber will be speaking later today, have done much interesting work on the connection between neural net architecture, particularly ResNet architectures and PDEs. Their relationship to optimal control has been explored, for example, by Benning et al. And lately, very interesting approaches looking at the infinite dimensional cases of Fourier neural operators from Andrew Stewart and his co-workers at Caltech. Which provide, all of these have the common theme of designing networks based on PDEs. To some extent, the filters are localized because of convolution, although of course that can include multi-scale aspects as well. But what we were thinking about was designing global spatially varying filters, taking nonlinear diffusion as a starting point. A couple other things that are important to mention. So one of the interesting works in this area by a group of Dong in Beijing, PDNet, which looks at learning PDEs of a general form where the time derivative of a field depends on a function of the spatial derivative. So this general form covers quite a lot of known PDEs. And their aim is to design a feed-forward network that approximates PDEs from a solution of samples over time. So you have observations of a state as a function of space and time, and then learn an appropriate PDE that describes that. And the key components there are this idea of a block which contains spatial derivatives, and then a symbolic combination of spatial derivatives, multiplicative, and two powers that can be combined to produce many of the equations that we know in mathematical physics. Example of that, we applied this to the problem, just anticipating the problem we're talking about. That's the idea how it works. This top line here shows an anisotropic diffusion. You could possibly see that there is a spatial blurring going on there, which is preserving edges of the principal features and blurring within low noise regions or texture regions. And then PDE, you apply this, you hand this to PDENet, and it gives you back an expression in terms of the derivatives up to an order you can specify. So when we applied this to this anisotropic model, it tries to produce a proxy for that in terms of constant multipliers of spatial derivatives up to a specific order. And visually, it looks approximately correct. Of course, the effect of the division is not very strong here, but basically it's producing a global approximation. So there's no spatial variation. Yeah, so this bottom line is the model that derived from that, or even of each component. But in a way, it's not very, I mean, it's quantitatively doing a good job. And also, I mean, it's not really to be expected that you can approximate a spatial varying with global coefficients. Another interesting approach is the group meta-learning set of differential operators, and here the idea is to try to solve the Green's function. So you want to learn the inverse mapping, the Green's operator, which depends on parameters, the physical parameters of the PDE. And the problem is that this invariably be a huge dense matrix stored, and questions arise: how do we represent the output from arbitrary parameters, and how should we represent the training data? And among other ideas, there is something that looks akin to a encoder decoder style representation, where you have a redundant form of wavelet transform and its inversion, and then the learned components are representing a compressed form of the coefficients of those basis functions that represent the Green's operator. And then the second idea is to use training data, which is sets of samples which are varied both over the source of the operator, initial condition, and the parameters. And that's been applied to numerous general inverse problems in scattering, photography. In this setting, it's linear. But in PDE, that's not. Okay, so let's talk about some of the work that we're doing. So we were actually really began this. We were motivated by thinking of nonlinear inverse problems and what would be a sufficiently challenging but not too strongly opposed inverse problem. And we decided that one would be an isotropic diffusion process, which we define here as PDE, which is the time variation of a spatially varying, well, possibly spatial temporally varying diffusion coefficients with initial conditions. So the forward mapping in this case is the mapping from the initial conditions to the final state. So we represent this PDE operator as simply S by L of gamma. And in the isotropic case, things are fairly easy to analyze because this is then just the spatial Laplacian, and we do have a Green's operator here, but the kernel being the Gaussian. And so it's well known that the diffusion process over a time t leads to spatial blurring with a variance of 2. And so if you evolving with an initial condition of an image and evolving this over time just leads to a spatially homogeneous blurred image. But we're interested in the nonlinear case, so we'll say there's a scalar diffusivity, which we'll put in the interval 0, 1. And one of the prototypical examples is the Rhodomelic filter. There's a number of variations of that, but it's a convenient one where you make this diffusivity the reciprocal of 1 plus the square of the gradient of the image with a threshold controlling the effect of the magnitude of the image. And what this essentially means is that if the magnitude of the image gradient is large as opposed to 0, which means that there's no spatial blurring, and as we go into very small edges, this goes to 1. So this varies between Gaussian blurring and large image blurring. And so if you program this in Evolver, you see at least these quite powerful so-called anisotropic diffusion schemes. There are many, many others, but this is just a well-known example. And this has this property of sometimes called edge-preserving flow. And the idea is that the texture here is being blurred out faster than the strong features of the image, such as tripod edges of the figure. But as you proceed for longer and longer times, eventually all of the features are eventually blurred, and the end state is just once again a uniform image, or that could be a piecewise constant image. So there's no general solution for that. So we have to proceed numerically. And then we just proceed formally. We say that between two time states of the function f, we can say that the increments can be integral of the separator over time, and then we make the approximation that in this time interval it's constant. So we fix, we call gamma at time n, the mean or a sample point in that time interval. And so we just say that the increment is given by delta t times second order derivative. So this means that we can solve this just by a iterative sequence. So we can use an explicit scheme or an implicit scheme, and we know that the explicit scheme satisfy the CFL conditions, whereas the implicit scheme is unconditionally stable. But in terms of accuracy, it depends on taking small steps. But in the limit as delta t goes to 0, either of these schemes will solve the problem. So now we consider this mapping from the initial state to the final state as the concatenation of a sequence of these incremental steps. All right, so this now begins to give a clue where we're going, because this now looks like layer operators from the initial state to the final state. Before we look at that implementation, now we look at the inverse problem. So again, for the isotropic case, the problem is stationary convolution, so the inverse problem is stationary deconvolution. And of course, we know it's unstable, but just to reiterate why that occurs, if we were in the Fourier domain, because we have stationary convolution, it's a multiplication in the Fourier domain. And so the time evolution is given by the product of the Fourier transform of the initial state and the Fourier transform of the kernel, which is itself a Gaussian. So the inverse could formally be done by division. We just multiply by this exponentially growing function. But of course, this is unbounded, and so there's no spatial convolution filter which corresponds to this unbounded operator. And of course, it's also unstable even in the presence of a small amount of additive. And so we have to regularize. But let's just proceed formally with that idea. So if we were to take the Taylor approximation of this operator in the Fourier space, and we just make some discretization in time, so we say that the final time step is the product of intervals delta t, then formally we can say that this inverse operator is the product of these incremental operators. And as delta t becomes small enough by Taylor series, we would expand this, remove the higher order terms, and we see that converting back to the spatial domain, this just corresponds to an incremental operator where we now take the delta t times the negative delta t of the Laplacian. So we could call this the Green's operator for the incremental step. And this also corresponds with the inverse of the implicit update, because the implicit update was given by putting on the left-hand side the delta t minus the Laplacian and inverting. So to go the inverse, we just take the explicit form of the implicit, sorry, we take the exact form of the implicit update operator. And this then lets us suggest that we could invert this process by concatenating these incremental operators. Now, of course, we know it's unstable because the addition of any noise will be exponentially growing. Nevertheless, we could write this down as a formal incremental state, and we could say system, we could say that as limit as delta t goes to 0, this would solve the inverse problem. So now we're going to conjecture that we could write down for the non-stationary case a set of local non-stationary filters, zeta, which would have this same local form, so incremental form in time. And the key thing is those filters will only have local support, and for the non-stationary case, the concatenation of these filters will solve the inverse problem. And just as a remark, there's a classical process in image correction, image analysis called unsharp masking, which is normally written in the following way, that we say that the observed data is given by a small multiple of the difference between the observed data and a Gaussian smooth version for some Gaussian scale and some sufficiently small epsilon. And if by following that through in the Fourier domain, we would say that the unsharp masking is achieved by taking, by subtracting the plastic of an image. And sometimes that's done by analog methods as a simple way of sharpening the image. So what we're potentially doing is replacing the stationary filter by a non-stationary filter as a kind of unsharp masking, and then concatenating these filters to provide the inverse over the whole diffusion scheme. All right, so how does that translate to a network idea? So we go back to this explicit time stepping scheme, and then we reformulate this as a network by interpreting each domain's layer, Fn for the sample of the image time Tn. And we'll use this idea of a diffusion layer operator with learnable parameters, gamma, and we'll include the time step. So we write this layer operator d theta on the layer parameters Fn as this identity, like a ResNet style, with a time step and a learned diffusion curve. So for two-dimensional images, this amounts to learning the components of a sparse operator. So we write this LDT in its numerical form as weights on the diagonals, on these off-diagonal terms, and the central diagonal, the leading diagonal, is a negative sum over the off. This satisfies the property of the diffusion equation because the sort of have a null space of any constant function. And so this just translates to this ResNet style architecture where we take this learned coefficients of the off-diagonal operators, increment at each time step, and add the identity to it. So this would be for isotropic diffusion. We would just write these down. But now for nonlinear diffusion, the filters depend on F itself. So we can't learn them explicitly. So we now introduce the idea of an implicit estimator. So now we're going to say that based on the current state, the current layer values, we're going to write a neural network which learns the diagonal components of this diffusion operator. So what we use is a small convolution neural network applied to the image in the filtering line. And then when we want to do inversion, we can just run this process backwards, but we know that we need to include regularization. So we're going to assume that we are going to add a smoothing operator to do this incremental backward diffusion step, which we'll write in terms of this generalized matrix W. So now this actually, sorry, I should correct that. So now this has this extra component on the diagonal. So now the learned diffusion, nonlinear diffusion looks like this. So we have this. This is where this is the trainable part of the network, where we're learning a neural network which learns the components of this filter. The filter is specified explicitly in terms of the diffusion equation. Great. So given the layer Fn, the filters are explicitly estimated by a small CNN, and then applied in this explicit way. We're essentially learning the diagonal components. And here now we see in the unregularized state, we only learn 4 of them, and the 5th one is negative sum on the diagram. But in the regularized version, we remove this mean free condition, allow that to learn regularization as well. So I'll show results with both of those approaches. Okay, so let's look at some computational results for that. So we first of all just do a simple deconvolution experiment. So we just apply this to an isotropic deconvolution. So we set the diffusivity to constant. So starting with the disk here, Gaussian kernel convolution image. We're learning the forward problem. So in the Fourier space, this is like a Bessel function. The Gaussian is just also a kernel. Sorry, the Fourier transform of the kernel is also Gaussian with the reciprocal of the variance. Taking the product of those two, we get the convolved image. And the network output is correctly learning this process. Just looking at it in a bit more detail, starting with the initial image. We have the network which learns the weights and learns this Laplacian-like filter. We add the image and we get the next iteration. Here's the corresponding coefficients learned in Fourier space. So as we proceed in the network, we're learning more and more higher frequencies in this convolution kernel. We get to the final step here. And then we apply a final ReLU to enforce positivity. Now, the interesting part then comes when we want to apply this to nonlinear problems. We now look at the pro-pneumatic function, which we repeat here. And we are going to concentrate on this inverse problem of restoring an image that's been contaminated by noise. So we use this STL10 database, training test time 10 times tape. So this is some examples from that, and these are the results of just running a pro-pneumatic anisotropic diffusion that has this characteristic edge-preserving form where some of the texture is blurred out, but the edges are preserved. And then we add noise, and then we use to invert. And you can see that it's qualitatively doing a good job. So here's the original reconstructed and the residual, and here we compare with a standard UNet architecture. Doing the same job of taking the pairs of the original and the diffused image and training a UNet to invert it. And of course, they look qualitatively very similar. So the question is, what differences can we see? Sorry, that's no noise here with 1% noise. So what is the difference here? So updates in internet are explicitly, and we're only learning, we're only using training and learning to produce these filters. And then we can be somewhat flexible in how we impose constraints on the filters and on the differential. So this is making use of our understanding of the problem we're addressing as opposed to a purely data-driven process. Then there's quite a difference in the learnable parameters. 5-layer DeathNet has 100,000 parameters, where UNet has 50 million. So we're using only 0.3% of the parameters in this case. We can also look at the error versus the training size. So for the same number of samples in the training data, the PSNR from the different is much larger than with UNet, although eventually they're converging to similar values in the limit of very large trees. Similarly, in the inverse problem with no noise, we constantly have a higher PSNR, especially in the case where we have low numbers of samples, which is one of the advantages. In the inverse problem with different levels of noise, we're seeing, again, consistent effects, but here the convergence comes earlier on, and with the higher noise, the similarity in the performance becomes more apparent with less number of samples. Another aspect is that we have an interpretable way of understanding the regularization. So by having this explicit form of this W, we can decompose into the differential part and the regularization part. So the regularization here just consists of a Tikhonov variable, because it's just on the diagonals of the, or let's say we're interpreting it in terms of the difference from the zero mean. Of course, in practice, you're learning some of the off-diagonal components, so that they can also be have spatially varying regularization. But what we would expect is that the difference from the zero mean increases with the level of noise. So we estimate this by taking explicitly sum of the off-diagonals minus the diagonal and taking the norm of this. And we do indeed find that this the magnitude of that regularizer, which has been learned together with the operator, is increasing with the noise level in approximately quadratic form, which we would expect with an L2 loss. So I guess one of the points I'm saying is that we have some greater interpretability about what the inversion operator is doing in terms of the components of an non-stationary diffusion process and a regularization process. Okay, so we also looked at the idea of looking at experimental data. So this is a experiment. So these are a little bit preliminary results performed by Giuseppe in conjunction with Charles Bell House at UCL, which is a biomedical research center. They have a number of physical funnels actually designed for ultrasound imaging, but they produce materials which have this kind of scattering density, which is spatially varying. So it's not easy to quantify that, but it is relatively easy to control the average scattering and some spatially varying aspects like the minimum and the maximum scattering and this spatial variation, spatial frequency variation. The idea was we produced a number of these samples, and the experiment is very simple. It's just put down on top of a tablet, and then we can put images through this and observe them with a camera. So I'll just show you one or two aspects. So here is this is experimental training. So this is one form of this, which is diffused, and you can see here. So this is putting this EMNIS database through, and you can see that we're getting quite noticeable spatially varying diffusion. When we run the inverse process with DiffNet, we're getting qualitatively good recovery. UNet is also performing, but appears a bit more blurred. And this, which is called interpretable DiffNet, is the version with the mean free operator without the regularization added. So this is produced, you can start to see the noise accumulating or appearing in this inversion process. Then just some more examples. So in these examples, the average spatial diffusivity is varying over the image, so is increasing. This one is relatively weak scattering, although you can still see spatial variation. So both definite and UNet are performing pretty well. UNet are performing pretty well. Increasing the blurring, increasing more. So this has probably pushed it beyond the limit of what it can achieve. We look here though, this is still doing recognizable deconvolution, and somewhat better, I would say, than UNet. Although it is, I mean, it's very difficult, I think, to perform completely fair comparisons. But one thing we can say is that the UNet with many more parameters requires a much larger training set. Now, I want to just move on time to some generalizations of this to other PDs on specifically other image flows. So let's going back to this stationary convolution problem again. We already wrote this. And let's write the kernel of the convolution in terms of canonical function and the scaling, representing the spatial width of the filter in a general way. So again, for the spatial convolution, stationary convolution, we have the Fourier transform result, product of Fourier transform of the field and the kernel. And then our hypothesis is that we will decompose this into concatenation of this canonical feature of this canonical kernel n times. And so that implies that the scale operator H hat sigma is just the power n of the canonical. Now, if we now look at the Fourier transform, if we look at a Taylor series for the canonical function, we can write it in terms of derivatives of the Fourier domain in the normal way, and multiplied with powers of the spatial wave number k. And we'll just use this notation to represent the m-dimensional version of the wave number. So now this, moving back to the spatial domain, that means that we could represent this incremental convolution in terms of a magnitude operator, an advection term, a second order term, and so on, where these are the coefficients. So in the diff note that we showed previously, we were only learning this term. But now maybe we can generalize it to learn other terms. And this gamma is now formally will be dependent. In the stationary case, we could work this out explicitly in terms of the moments of the Fourier transform of the kernel. But now let's think of it in terms of a network. So let's consider a filter operator which produces this jet of derivatives in all its multinomial factors. And now we consider a learned operator for associated with each of these. So we could come up with this generalization which says that the incremental step is a time step times a set of weightings for each of these. And the summation of that over all of those variables will be the incremental step. So in terms of a network, this would look a bit like this. But each layer we would take f, we would take an explicit derivative to derive the derivatives up to chosen order. And then we would learn this multiplication, these multipliers and multiply them together. And then in this dotted line, well, we could consider whether this learned operator is learning from the image itself or whether it's explicitly learning from the derivative. This might provide a faster training. I'm not quite sure yet. So we'll call this a d lambda block of a general architecture. So if we truncated this at J2, then it would be very similar to DiffNet with the addition of this advection. We'll be learning these coefficients plus these coefficients. And if, again, whatever order we truncated that, we would be enforcing a minimum number of vanishing moments. So now, again, we would then just conjecture that the inverse process could be replaced by learning a different set of coefficients, which was still dependent on the same derivatives of the image, but in the reverse direction. So again, for the stopping at order 2, we'd be learning these coefficients where now we've changed the sign of the advection. All right, so this was the idea for and he did a number of architectures which encode this idea, which we take the original image, producing the jet derivatives, and then learning these coefficients to add it to the generalized form. And this turns out to be similar to some other kernel estimations for variable convolution and some papers on image processing. Also, we considered how to achieve a multi-scale aspect by, as well as producing the image derivatives, producing the downsampled versions, learning the coefficients at each of those downscales and adding them back into the diffusion process. So 2 examples of trying to use that. And then if we look at image warping, we can represent it as just a transportation for a known displacement field S. So here's a sample of a spatially varying warp cameraman. And we also, well, out of interest, I wanted to apply this to something more nonlinear. So this affine shortening flow, which is the rate of change in the images proportional to the cube root of the curvature multiplied by the gradient of the image, which has this expression here. This is another kind of image enhancement process which looks to flatten the level sets of the image. So we produce training data of that. So here's an example for the affine shortening flow. So what we're trying to do is, so this is the ground truth, and this is the affine shortening flow of that ground truth, and we're trying to learn these inversions steps. So here is UNet's version of it. Here is the previous DiffNet, gradient DiffNet, and multi-scale DiffNet. So these cases it's not so easy to see qualitatively which may be better. We'll also look at quantitative results in a moment. Here's the warping example. And here we can see some more clear differences. So here's this input is the warped image, warped and slightly diffused version of the ground truth. So UNet is surprisingly, as often the case, doing fairly well. DiffNet also does fairly well. And here the multi-scale DiffNet is really showing quite some improvement. And quantitatively, we find that that's the case. So for the warping result, yeah, the multi-scale DiffNet outperforms also for the pronomalic, not for the affine shortening flow. And surprisingly, for the affine shortening flow, the original DiffNet. So this is a not this is a little bit of a positive at the moment because this original DiffNet only has the second order derivatives and doesn't include anything which can represent the powers of those. So I'm not really sure how that works. Okay, so to summarize, the idea is that we're taking physics into account to obtain more expressive network architectures, which allows us to constrain operators based on our knowledge of the processes which we emulate. One thing we definitely observe is that we have a reduction in the number of parameters required, which allows us to have an increased interpretability. There's a lot of aspects we still need to understand. We need to analyze stability estimates, and the regularization schemes are still somewhat simplistic because they're just relying on the regularization being learned through this already present structure. Whereas, of course, we could add some other regularization scheme at the end of the process. For example, a learn regularizer, denoising regularizer. But again, this would detract from interpretability. Should also mention that the idea of having spatial variation network is also not new. It relates to lots of work done on attention layers, which essentially provides a multiplicative weighting to the learned network. But we started working on that. I haven't got any. I want to look at other flows that we can write down in terms of image operations, image-based PDEs, and eventually to look into dimensions higher than 2. And another possibility will be to, because this multi-scale aspect seems to be quite powerful, to make a connection to the use of the wavelets approach. Wavelet schemes obviously don't have an explicit interpretation in terms of spatial derivatives, but they qualitatively bear a relationship. Okay, and so I think I'll stop there. At the end, and if there's any questions, I'll be happy to take.
So I'll kick off, Simon. Just all of your.
All right, great. Go on.
Sorry?
Yes, that's fine. Yes, go ahead.
All of your problems have worked with second order operators, and you've got maximum principles and stuff floating around to help you. Can you extend this to the fourth order operators you use in image processing?
Well, they weren't entirely the. I mean, we also had the warping, which was first order. But yeah, there's no reason why that shouldn't be done. I mean, the gradient diff net does include operators of any chosen order. Okay. But we didn't test it on any explicit higher order data. But I think there's no reason. I mean, there's no. We're not relying on the maximum principle anymore.
Okay.
Thank you. Yeah. Yeah. Well, that's of course true, but we can't estimate that very easily. But for the diagonal term, you can explicitly get it from the deviation from the I don't know. I mean, I was thinking the same thing. There could be some effect. I mean, honestly, there is. Yeah. But then it's an interpretation. Are you learning? Are you interpreting that as learning the components of that derivative operator, or are you learning? don't see a way to stop that. But at least from what we saw in the result, there is a clear relationship between the diagonal the deviation from the mean on the diagonal and the noise level, which is something expected. Yeah. Oh, Chris couldn't hear the question. Oh, sorry. I don't know. I don't quite understand. I guess we're using this mic. Yeah. Yeah. So maybe you need to. Yeah. 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 Oh, right. So the question is it possible? That is possible. I mean, there is practical math which does do that. Obviously, implementation of that is quite tricky because you have to include memory effect over time. You can't just do it as you could do it in a very domain, of course, but that. Okay. How do we know this? Yeah, the question was about fractal derivatives. And yeah, I mean, there are fractal networks. We haven't. I mean, that's definitely would be interesting, particularly because the A5 shortening flow or other of these curvature flows technically use powers of the derivatives. So when we applied it, I mean, we weren't exactly expecting to see that it would work, but it's an interesting question that people address at these learned PDs. And in general, you observe some physical problem and you want to learn a PD. Can it be expressed in terms of integer powers of derivative operators or in terms of fractional powers? I guess it's not known, but I mean, it's a relevant question to ask. I mean, I would like to extend it to that. I'm not sure the best way to do it.
So when you use it for deconvolution, can you visualize the convolutional curls that you learned?
Yes, we did. I mean, I didn't include that here, but yeah, we can do that. And then generally speaking, I mean, you're finding that the higher frequencies are appearing later in the network. I mean, yeah, I think those are in the paper. But again, explicitly interpreting them, I'm not quite sure. I mean, but probably the thing would be to design more carefully some phantom units, test cases where we can predict what we would expect to see. Yeah. Yes. I haven't really thought about that. You were saying it's non-Markov. Oh, sorry. Because of the skip connections, yeah. So the question was about the fact that UNet is non-Markovian because of the skip connection. But on the other hand, I interpret DiffNet. I mean, all of the scales in DiffNet are used. I mean, it's not really interpreted in terms of time evolution, right? But if you were putting a UNet incrementally in time, it would still be first order. So it would be Markovian in that sense. Obviously, some work has been done on higher order schemes in time. Both and Halo have what's it called, HyperNet, which is second order in time, and you may be hearing about that later today. So basically, I think many of us at this program are interested in this whole connection between PDEs and networks. So when you write down the discrimination of PDE and implement it, and then you look at layer architecture, it's just often just language interpretation, right? But several of the things like resident, this is well known, right? Euler's some PDE, except that, or some ODE even, except that it's not explicit what that is. Now, so all we're basically doing here, if you're restricting our kernels to be explicitly derivative operators, then we have a more direct interpretability. But of course, we're not do that. But maybe applying it to inverse problems. Okay.
I think we are saturating here for now. Are there more questions from the remote participants? So by the way, we are going to go now into the coffee area of the INI and have coffee. So I'm going to take my phone with me, and so I can take you with me as well to the coffee area. We did that also last week, so we are going to communicate with you over the phone if you wanted to stay on and have a chat. You can take us anywhere.
But I should log out.
Yes, I will.
I'll log out of
Yeah,
this. Maybe they stop the. Maybe they stop the recording. Okay. Thank you, everyone. I'm going to check out, but apparently we can stay in. So.
Well, great stuff, Simon. Thank you.
Great. Maybe see you later.
Bring your own. I mean, you also bring your own.
This is only us.
Hi, Martha. You actually said very good.
Send out a package.
One second.
Yeah, don't, if it doesn't work, just drop us.
No, it works. Actually, yeah, Chris is also, it's just that I'm on my phone.
Your mic for Simon's audio.
Yeah, I think we need to
computer.
change something with the audio. Maybe
No, this is his
also,
computer.
yeah, now you can see who is actually here.
Hi. They can see the phone, that's great. But it's always good to wave to the phone.
Yeah, I think we need to solve the mic thing. Maybe each of us needs to connect via our own device or something like this.
Simon's microphone, I don't know what it is. I suffered under it for ages. So.
Yeah, I think he said he has a new laptop, but he hasn't gotten around to.
He has always the same problem. I don't know what
Okay, maybe this doesn't change this.
What I do, I
even the new laptop. I don't know.
I use this mic, and
So you probably recognize all of this here, right?
Yeah.
Oh, where are we heading?
We are heading to the coffee area now because we were actually in seminar room 2, so in the gatehouse.
Ah, right. No, you weren't in the INI.
We were in the INI gatehouse.
Yeah, the small one, I think, in the first floor.
Exactly.
How are you, Marta?
Yeah, I'm okay. Yeah, I actually wanted to ask Simon to understand exactly what he's doing. It's too quick for me. Chris, did you get this derivation of the? Did you get the analysis that they are kind of?
I need to go off and
Yeah, that's so
I'll hand you over to Simon in a moment. Then you can ask Simon directly.
I've written it all down. I'm going to go off and think about it.
Yeah, I know that it's the paper. I'm just trying to understand the idea behind it, really. So the principle, what is it trying to achieve in a sense of what is the limitation of the analysis to start with? Because I didn't quite understand. It was too quick for me.
Well, this is the general issue of all time. We're trying to discretize time PDEs and link that.
Good if I know how to log in.
the usual layered structure of a neural net.
But there is a question for you, Simon. You want to take my phone?
The expert.
Hello.
Hey Simon, can you take a step back and kind of explain step by step what you are doing, giving some intuition?
You want me to give the talk again?
No, because like, you know, so you can you just kind of explain, because this Green's function stuff, this was too quick for me. I mean, I have to say, so I didn't quite.
Well, the basic idea is the problem we're trying to emulate. There's the forward and there's the inverse problem. So the forward problem is anisotropic diffusion. So you know what that is, right? Like a peronomalic process.
Yeah,
right?
yeah.
Where at each update, the stencil, if you like, depends on the current state.
Yes.
I mean, not the shape of the stencil, but in terms of diffusivity, you're blocking diffusion where there's structure like edges. Okay, so then we want to replace that with a learned network.
The stencil, the coefficients of the stencil.
Yeah. So of course, if we knew, I mean, if that would be relatively easy to do, if we knew that it was peronomatic, we would simply write down the peronomatic expression and calculate the value. But we wanted to see whether it could be learned from data and have the same effect. And then if you can do that, well, then we can reverse it, because there's no, for the inverse problem, there's no known way of running an anisotropic diffusion in reverse, right? Mm-hmm. To invert the form of a edge preserving diffusion process. So we're relying on a learned network to do the inverse process. And then the idea would be, which I mean, I don't think we would claim we've achieved exactly. The aim would be to be able to apply it to any arbitrary kind of diffusive flow where we definitely didn't know which one it was. So if things were working, where we would like to get to would be, we're just presented with any kind of flow process, and we can learn to emulate that, and we can learn to do the inverse of that without having to know.
So how
the equation
how did you determine what is your flow process? Because you could, depending on, you could diffuse faster, if you diffuse slower, so you could have different ways to go from the image to the blurred image and reverse. So how do you pick this? Which flow are you doing?
Well, in the training set, you mean? So for the training set, we use peronomalic, but in the learn network, well, it just learns it itself. So we wouldn't
actually a peronomalic kind of thing. You're not trying to find a flow or with some properties, but you're trying to train it to learn peronomalic type of diffusion. Yeah.
That was the first case, and then we also learned advection terms, and then we applied it to this affine shortening flow curves as well to see, and it seemed to do surprisingly well even at that.
Okay, so what was this? What were the Green's function? The significance of this Green's functions?
Well, this was just a justification of why it might work, because in the isotropic case, you can write the Taylor series of the Green's function in terms of the moments of the Fourier transform of the kernel of the forward problem, and then in terms of convolution, that means that you can write it in terms of a set of differential operators up to whatever order moments you choose. So that was just a conjecture, really, which works out in the isotropic case. And we just sort of conjecturing that it will work in the general case. But I mean, the basic idea is that the Green's function for a long scale process of time, capital T, can be written as the concatenation of these local operators. Which is obviously true for a Gaussian, right? You can say that the Green's function for isotropic blurring is the n times concatenation of a very small blurring process, right? I mean, that's sort of facile, right? And so the inverse process formally would be the deconvolution would be the concatenation of these exponentially growing functions. So obviously it's unstable, but you could possibly represent it in terms of those learned steps, as long as you admit regularization.
But the anisotropic part in this interpretation, how does this come in? It would mean that you would have more concatenation in one direction than in the other of the small Gaussian.
Yeah, that's what would, but I mean, and also more spatially varying, right? I mean, you would have a smaller and a larger blurring in different parts of the image depending on the structure. I mean, I don't know if you could look at the paper where some of that's written out. But.
I know. Okay, thanks.
Okay, I'll give the phone back to you.
Hello again.
Okay, yes, thank you.
Skipping a meeting.
Simon is skipping a meeting. This is good.
Okay, this is wonderful.
Yes, this is good.
Right, I'm going to disappear in a minute, but that was a really good seminar.
Thank you. Yeah, tell it to the speaker, but I guess, yeah, I'll tell it to him.
Try to get, one of those USB microphones or something like that, if they have something lying around.
I use this for stuff. It's a sort of kind of desk mic, which
I think at the moment, yeah, so what we should maybe change is, because at the moment, I mean, this was only our second seminar in a way. We let the speaker use their own laptop, and so we're kind of relying on the mic that they have. But
bring it into.
I think Carola is saying, Chris, that they have the room mic'd up, just that Simon's hardware disabled the access.
Oh gosh, yeah. Classic.
Okay.
Oh well, it happens.
I think for the participant questions, maybe each of us needs to join with their own device or something. Yeah. I don't know. Let's see.
The alternative is to have a kind of something that is like fairly. They should have something in Isaac Newton, like a conference style, teleconference style device, something like that. It cannot be too directional. It cannot be too, if you have a condenser mic.
I mean, usually in seminar room 2 in the Gatehouse, they also record the talks, no? Or maybe they don't. I don't remember this. I mean, in seminar room 1, they definitely have it. And for Matt's talk, the microphones were actually working, I think, no? We could ask questions in the audience and everyone heard us. Yeah. It was, they just, I don't think they have this in the small seminar room, but we can ask them. Yeah.
Anyway, thanks a lot for going to all these lengths, and I will leave you to have a coffee in peace now, offline.
Well, thanks for joining, Marta. Thank you.
No, I last time I just missed.
Maybe you could give us a tune sometime, Marta.
Sorry?
You could give us a tune.
No, I am. I am not really good.
You've got 2 keyboards there.
Oh, you see my second one. Oh, yeah, there's a new one. That is actually that will take some more doing, because there's actually a Hammond organ. Ooh. So it's it's even different and even more annoying if you can play it. It's like the organ is a quite different technique, because it is a sustained instrument, so like strings. So you have to crawl your fingers and stuff like that. So it's like, anyway, so that's, it's a kind of new project. No, but I did actually play for people at Isaac at Oberwolfach. But only those who happened to be there and didn't want to leave. I think Todd Quinto and I think Peter was there maybe. And so
I've only been able to go to Oberwolfach remotely.
They have the Steinway piano there. So actually there was like that. I was sitting at the Steinway piano. They just came and they didn't want to go. But honestly, I am not a good, I play better guitar actually. But I started piano to understand the music theory.
Sounds good to me.
Okay, I will leave you to it, no? Take care. Ciao.
Marta, come here soon.
It's just such a mess.
Yeah, no, I know. Probably
And
with
we are
Max,
a
it's,
bit worried, so
more
because
complicated.
Max is not vaccinated and he is on top of everything. And school we didn't have any choice. Otherwise, if we have choice, we don't really know what is going on with the.
Yeah, no, I totally understand.
I mean,
Yeah. It was just kind of, unconditional expression of emotion that it would be nice that you're here.
I know. And Carola, we are doing this, we're doing this one for 23, and I really I'm so annoyed that what happened to you because it is so much work.
Yeah.
I'm so sorry for that.
Well, we'll make the best of it. We'll make the best of it.
Honestly, I know I kind of said that I want to participate for most of the times when I'm on holidays or something like that, because it's just great that you can connect us,
Yeah.
I know it doesn't feel right, but it's still good.
Yeah, I mean, somehow I think because we know each other, it's easier. I think for those, because there are so many people from different communities coming together, it's harder. You can also see that.
My is going to come. He really wants to come. He's going to stay in INI accommodation. Thanks for the tip. Because I told him, I told him, if you go to the country, you're most probably going to be completely alone.
Yeah.
So, but then with the INI accommodation, if there's anyone there, they are going to be in there.
Yeah.
So that he doesn't have this, he went to Bath, Chris. He's your best student of Bath.
I can't hear you. There's extra noise. Who went to Bath?
My PhD student. He was Paul's student.
Ah, right. Yes.
He got the award for the best something.
Well, they all do.
And anyway, so he's working with me a little bit on the nonlinear wave equations, and so, but he wants to learn something about that.
Well, nonlinear wave equations are immediately interesting to me.
Yeah, we have learned that weekly nonlinear wave theory. It took us through Russia everywhere. It was interesting.
Yeah. Well,
it took us a long time to actually find the bearings.
I never remember my Zoom login.
Well,
because you need to log in with your Zoom.
I will, Chris.
You use the link, you still need to log in.
I think maybe I will drop you an email.
That would be terrific. Yeah.
I will drop you an email because I would appreciate some hints for if you have been playing with Burger equation.
I logged in. I
spent my life on Burger's equation.
Yeah, I would appreciate some tips. I will tell you where I'm coming from and what is. If you could give me some pointers, what are my options? Would be great.
Well, I claim to have a good scheme for solving equations.
No, yeah, but I'm also into analytical solvers. I will explain as far as I kind of.
Well, that's fantastic.
Guys, I'm going to leave you to this discussion.
Yeah, Carola, just I'm going to get to business that we discussed yesterday.
Say again?
I'm going to get on with the business that we discussed yesterday.
Yes, perfect.
You know what I mean?
Perfect. Great.
Wonderful. Excellent coffee experience.
Yes. I will write you an email because I actually have a meeting now already overdue. But
I'm actually going on leave later on this week, so if you write it now, I might be able to say something, but if you leave it till later on in the next month, I'll be able to give it a much better response. I'm just trying to.
Okay, then we do it. Okay, because for now it's for the next month project essentially. The student right now writes some kind of write up. a milestone write-up. So at this moment, he writes anything about this because there's a future, but kind of what we do later really matters. So maybe when you come back from holidays.
Well, that'd be great. But as I say, I spent a lot of my life looking at Berger's equation and some things, because these are the equations that come up. I mean, they're prototypes, so the sort of meteorology type equation.
Exactly, but we actually have one. But the key is that how we get the convoluted way to get this Berger equation, so to speak.
Sure, yeah, well, that sounds great. Okay, brilliant. Well, maybe we might even be able to meet up at some point.
Yeah, maybe. Let's see what the government managed to screw up.
Well, I'm sure you know, but Simon Corolla and I have got this grant, so we'll be working closely with each other over the next 5 years. So I'll be coming to UCL a lot.
Yeah, fantastic. I managed to get two PhD students this year. So one is going to do something that's not quite machine learning, but the other one is going to start on Helmholtz and machine learning. But I want to go through the TIMO type of approaches and look for machine learning in there, so to speak. So the kind of
this is a game we're all interested in now, of course. Yeah. I mean, gosh, I've just had one of my PhD students finish who spent 4 years looking at the Helmholtz equation. She wrote a 400-side thesis, which I'm slowly recovering from. But yeah, it's a really nasty equation, Helmholtz. It looks pleasant, but it isn't. It's really nasty.
It is, and but like my impression is that there is a lot of self-similarity in it. Some sense.
Well, yes and no. I mean, the problem is it's linear, and I hate linear equations. You've got no feel. There's no structure to them. Non-linear equations, you've got the extra structure from non-linearity, so that's already makes them hard for me. But there's no obvious self. I mean, you've got translation in space, translation in time, rotational symmetries, but you've got no scaling symmetry, which is one I always look for. That's why I hate I mean, I don't like linear equations for that reason. There's no implicit scale in them. Yeah. Anyway, lots to be said.
All right. Okay. Great.
I mean, the way I approach it is the way lots of people approach it. Of course, is to use the iconal equation as the first approximation, and then start with that.
Yeah, we did do a lot of. I mean, I had a whole student who did develop the kind of ray type of ray-based approaches, but they are not rays. I mean, they are. We think of this as taking the Green's formula solution for the PDE and then approximating the Green's function along the rays.
Okay. Yeah.
And then it breaks, of course, once the caustic theoretically appears. It breaks, but in praxis you can you see these solutions, you see this complex shift happening in this that you don't have a way to interpret along the rays, but it still makes sense to integrate it in the paths framework, so to speak, gives you better results. But so that's the kind of that got me into it. So that what this non-linear guy is doing is also working with rays. What
sort of frequency are you at? I mean, I was looking very high frequency Helmholtz.
So what the acoustical kind of ultrasound type of Helmholtz for the breast CT, for example.
Right.
Yeah, I mean you would have to solve it in for the range of frequencies because I mean at least in a kind of standard way when they do it, because otherwise you get all kind of sort of phase issues going on. I have not been working with Helmholtz yet, so that's the kind of the new type of it, but I have a husband with a lot of experience in that matter.
Yes, I suppose that's handy. I don't know. My wife works in such a different field for me. Mind you, my son is into all of this stuff now. He's doing Laplacian machine learning stuff. His PhD.
Yeah. Right. Okay. Everyone is doing it essentially. It's a very popular thing.
I think Gil Strang said something along the lines: if you're not doing machine learning, then you're losing. You're going to be behind. It's the area which everyone should be in at the moment. And I think this thing with Simon and Corolla is looking at machine learning in the context of differential equations. So I'm sure we'll have lots and lots to talk to you about over the years. That'd be fantastic. Yeah. Good. Well, I mean, I look forward to your email, and I look forward even more to hearing you on the guitar.
Right. Okay.
That'd be super. Where do you live, by the way? Are you in London or?
I am in Barnet, in your old place.
By where I was born. Sorry, we must have had this conversation. Yeah,
We did. Yeah, we had our previous flat was here, and then we bought a house the same area. I mean, you know where St Albans Road is?
I was only 4 when I left Barnet. I don't really remember it very well, but I was born in Friam Barnet, which is where I was born, which is a bit nearer. I mean,
it's a different.
It's a little bit different, and then we lived in Harrow for a long time, and then we moved up to Hertford, but all in the same sort of North London-ish area.
Yeah.
Okay, I need to get on with something, but really nice to talk to you. And it's one of the nice things about all these things, of course, is that we can interact reasonably well with Zoom and so on.
Yeah. Let's see what if the government maybe doesn't manage to screw everything up, maybe we can turn the corner finally.
Well, I hope so, and I want to see my son again, for example. I mean, he's been stuck in Holland. He's in Delft.
So I haven't seen my family for a year and a half, I think.
Yeah, no, not good. Okay, well, take care and see you soon.
Okay, see you. Thank you, Grace. Bye.